Have you ever thought about how a star dies, not with an explosion, but with silence? Imagine a sun that has burned for trillions of years, its light fading until not even a trace of warmth remains. What's left isn't a glowing ember or a swirling cloud, it's a dark, cold remnant called a black dwarf. Theoretically, they're out there somewhere, waiting in a universe old enough to let them form. But here's the twist. We've never seen one. Not yet. The reason why might surprise you. If quiet mysteries like this one make you curious, a small like or subscribe helps more minds join the search. So, settle in and let's explore what black dwarfs really are and why they carry such a haunting name. There will be a moment unimaginably far ahead when the last light of the cosmos appears. It will not come from a living star, or from a swirling galaxy, or from the hot blaze of a distant quasar. The final spark will rise from something we have never seen and, in practice, never can. A stellar corpse, so old, so cold, and so overlooked that it would make our sun look like a newborn. That last light will be the flare of a black dwarf supernova. Today, the universe is about 13.8 billion years old. That sounds vast, but on the scale we are about to use, it is closer to an opening heartbeat than to a full lifetime. The timeline ahead stretches beyond normal thinking. We will move through ages so long they bend intuition. Stars end, galaxies thin and fade. Even atoms may not last forever. And at the very end of that path, there is one more act left for a quiet remnant. Black dwarfs do not exist yet. They cannot, because the universe is still young. White dwarfs need unimaginable spans to cool and darken. Only then, after their heat has leaked away, can they settle into true blackness. In a future so distant you would need around 40 digits just to write the year, every sun-like star will have taken that route. Each will become a cold, dense relic of a brighter age, drifting in a night that no longer has much to give. And then, after waiting longer than the current age of the universe repeated a trillion times, a few of these dead stars will explode, over mind-bending spans. Nuclei inside those dark stars can still meet by quantum tunneling, a tiny chance event that becomes inevitable when given enough time. Slowly, step by step, lighter elements fuse into heavier ones until iron accumulates in the center. Iron cannot give off energy by fusion, so once enough of it builds up, the support fails and a sudden collapse triggers the final blast. These will not be the familiar supernovas we see in young galaxies. They will be iron supernovas, events born from quantum mechanics still doing its job in a universe that has run out of easy energy. They will be the last fireworks in cosmic history, a proof that change can still arrive, even when almost nothing is left to change. To see how this could be true, we need the story of how ordinary stars live, end, and remain. We exist in what future historians of the sky might call the stelliferous era, the age of stars. It is a bright interval when hydrogen fusion powers countless suns, making light and heat and the heavier elements that build planets and eventually life. This era, vivid as it is, will not last. On deep timescales, it is already late afternoon. Star birth has been slowing for billions of years. Gas that once fed new stars is locked into old ones or blown out of galaxies. Start with a star like our Sunday. It has been shining for about 4.6 billion years, which is roughly a third of its full life. In its core, hydrogen nuclei fuse into helium. That fusion releases energy, and that energy becomes the sunlight and warmth that make our world possible. The process is steady and efficient. Every second, the sun turns about 600 million tons of hydrogen into helium and loses roughly 4 million tons of mass in the trade. The missing mass becomes pure energy by Einstein's relation between mass and energy, E equals mc, 2. This will continue for about 5 billion more years, and then a bottleneck appears. The core runs low on hydrogen fuel. As the fuel dwindles, the core contracts under gravity and heats up. The outer layers respond by expanding. The sun swells into a red giant. Its size will grow so large that Mercury and Venus are almost certain to be swallowed. Earth may be, too, depending on how much mass the sun sheds and how Earth's orbit shifts in response. Even if Earth escapes being engulfed, the heat will strip the planet and boil its oceans. In the red giant phase, the outer layers are only loosely held. A strong solar wind peels them away. The gas drifts outward and becomes a planetary nebula, a shell of glowing material lit by the hot core. It is not a planet, despite the name. Early astronomers used the term because these round shells looked planetary in small telescopes. The patterns can be simple rings or complex shapes sculpted by magnetic fields and by the star's spin. When the wind and light settle, what remains is the core itself, now exposed. That core is a white dwarf. It is about the size of Earth, yet keeps around 60% of the sun's original mass. The density is extreme. Imagine compressing a school bus into a sugar cube. A teaspoon of white dwarf matter would weigh about 15 tons on Earth. Physics there does not behave like physics in a normal gas. The pressure holding the star up does not come from heat. If you heated it or cooled it, the main support would barely notice. Gravity pulls inward, but a different kind of pressure prevents collapse. A white dwarf does not produce new energy by fusion. It shines because it is still hot from its birth. Think of it as a hot ember that slowly cools in open air. A fresh white dwarf can have a surface temperature above 100,000 degrees Celsius, which would make it appear stark white or bluish white in a telescope. At first, it cools quickly, then more slowly as its heat leaks out through the thin atmosphere. Over billions and then trillions of years, it radiates energy into space and becomes dim. Nothing reignites it. Deep inside, as the temperature falls, the ions, mostly carbon and oxygen for stars like the sun, begin to line up in a regular pattern. The white dwarf starts to crystallize. You can picture this as the interior becoming a rigid lattice, a kind of cosmic diamond that slowly grows from the center outward. Crystallization releases a little extra heat, which briefly slows the cooling, but not for long on cosmic scales. Given enough time, the entire white dwarf becomes a solid object, still dense, still faint, still slowly fading. What keeps a white dwarf from falling in on itself is a quantum effect called electron degeneracy pressure. Electrons are tiny particles with a rule. No two identical electrons can share the exact same quantum state. This is the Pauli exclusion principle. When matter is squeezed to the densities inside a white dwarf, the low energy places for electrons fill up. Electrons are forced into higher energy states, which creates a pressure that fights gravity. This support does not depend on temperature, which is why a white dwarf would remain supported even if it were cooled to near absolute zero. It is pressure from quantum rules, not from heat, that holds the star up. Because of that support, a white dwarf is stable until something else changes. If you add too much mass to it, past a limit of about 1.4 times the sun's mass, called the Chandrasekhar limit, it cannot be held up by electron pressure, and a different fate follows. In close binary systems, Steady stealing of gas from a companion can push a white dwarf near that limit and lead to a thermonuclear supernova, the kind astronomers label type Ia. But typical isolated white dwarfs never reach it. They simply cool for trillions of years, moving from white to yellow to red to a faint infrared glow. Eventually, they will be so dim and cold that they blend with the dark of space. At that point, we would call them black dwarfs. The Milky Way already holds an enormous population of white dwarfs. Any star with a mass between roughly half and 8 times the mass of the Sun will end this way. More massive stars go another route. They rush through their fuel, explode as supernovas, and leave behind neutron stars or black holes. Smaller stars than the Sun burn so slowly that none have yet reached their end. The universe simply is not old enough. The sweet spot for stellar endings, the most common track, leads to white dwarfs. Surveys of nearby stars and of star clusters show white dwarfs scattered throughout the galaxy, each a quiet record of a star's past. Astronomers have observed many of these remnants. One orbits the brightest star in our night sky, Sirius. It is called Sirius B. It has nearly the mass of the Sun, but is packed into a sphere smaller than Earth. Another well-known white dwarf is Procyon b, a companion to the bright star Procyon. And there is 40 Eridani b, part of a triple system and the first white dwarf recognized as such in the 19th century, long after William Herschel noted the star in the 1700s. These objects are not rare curiosities. They are common outcomes of stellar life. The nearest known white dwarf to Earth is indeed Sirius B, only about 8.6 light-years away when you measure the distance to the Sirius system. It circles Sirius A roughly every 50 years on an elongated path. Despite its similar mass, it is tens of thousands of times fainter than its bright companion, which tells us how small and dense it must be. If, in a thought experiment, you could stand on its surface, your weight would increase by millions of times compared with Earth. The surface gravity would crush anything familiar into a thin, compressed layer. Even the light leaving its surface is shifted by gravity, a small but measurable effect called gravitational redshift. White dwarfs are not all identical. Their appearance and spectra depend on what elements float at the top and how hot they still are. In many white dwarfs, the outermost layer ends up made of the lightest element available. Because gravity sifts material, heavier atoms sink and lighter ones float. A thin skin of hydrogen can therefore dominate what we see, even if most of the star is carbon and oxygen underneath. The youngest and hottest often show hydrogen in their thin atmospheres and are grouped under the label Da. In these stars, hydrogen absorbs certain wavelengths of light, which stamps a pattern called spectral lines on the light we see. That pattern lets astronomers classify the star and estimate its temperature. The hottest and youngest are called Da white dwarfs, dominated by hydrogen in their thin atmospheres. As white dwarfs cool, the mix we see at the surface can change. Some end up with helium-dominated atmospheres and are labeled Db white dwarfs. Others display faint fingerprints of carbon, oxygen, or even heavier elements. Astronomers call them metals in their spectra. These fingerprints appear as narrow dips in the light at very specific colors. Each element absorbs light in its own pattern, like a barcode, so the lines tell a careful reader which atoms sit in the thin outer skin. Those signatures are not just labels. They are clues to the star's past, how the outer layers settled, how much mixing occurred, and what nuclear reactions ran in the parent star before it shed its shell. Surface helium suggests that hydrogen has sunk or been blown away. Traces of carbon or oxygen can mean dredge up from below. or a past event where the star swallowed dust and rubble from old planets. Yet, the atmosphere is only a skin. Beneath it, a deeper transformation unfolds, one that turns these compact remnants into the largest diamonds the universe will ever make. When a white dwarf is born, its interior is a dense, hot plasma made mostly of carbon and oxygen nuclei. Think of positively charged nuclei embedded in a sea of degenerate electrons, the quantum-supported electron gas that supplies most of the star's pressure. Right after formation, the nuclei zip around with high thermal energy, colliding and vibrating in the leftover heat from the last phases of fusion. The electrons fill up the lowest energy places they can occupy, pressed by gravity into a tight arrangement where the Pauli exclusion rule keeps them from all piling into the same state. As the white dwarf radiates its heat away over billions of years, the thermal motion slows. The electrostatic attractions between nuclei, each nucleus tugging on its neighbors, do not weaken, but the random jostling does. Bit by bit, the balance shifts. The electrical pull becomes stronger than the jitter of heat. At that threshold, order begins to appear. The nuclei settle into a crystalline lattice, an organized arrangement in which each one sits in a repeating pattern relative to the others. The coolest region is the center, so the process starts there and moves outward like a freezing front. The white dwarf solidifies from the inside out, turning the liquid-like ion soup into a solid framework of carbon and oxygen. This is not a figure of speech. The crystal structure mirrors the one we know from diamond on Earth, a face-centered cubic lattice with each carbon linked in a tetrahedral pattern to 4 neighbors. The physics is the same, only the scale changes. The white dwarf becomes a cosmic diamond, not clear and sparkling like a gem in a ring, but rigid and enormous, a planet-sized crystal carried by gravity. On Earth, a large diamond might pack around 10 to the 22nd power carbon atoms into a single gem. A fully crystallized white dwarf contains roughly 10 to the 56th power carbon atoms knit into one vast structure that spans an object the size of our planet. The number is hard to picture. Another way to say it, if you multiplied the atoms in a huge Earth diamond by a trillion, you would still be short. We cannot dig into a white dwarf to see that lattice, but we can detect its effects. In 2019, by combing through precise measurements of white dwarf brightness and color from the Gaia spacecraft, researchers found a clear pileup. Many white dwarfs were a little brighter than simple cooling models predicted for their color. The straightforward explanation is latent heat, the extra energy released as the interior changes phase from liquid to solid, just as water releases heat when it freezes into ice. That extra heat stretches the cooling time and lifts those stars slightly above the smooth path we would draw for a star that cools without changing phase. This phase change does not sweep through in a single moment. The solid core grows over hundreds of millions of years, surrounded by liquid outer layers. Between them sits a mix zone where crystallites form, melt, and reform at a constantly shifting front. The makeup also sorts itself. In many models, oxygen, being a bit heavier, tends to concentrate more in the solid, while carbon becomes more common in the liquid, and then later in the outer parts. That sorting can alter the star's heat flow and slow the fade even more. As cooling continues, the front marches outward. Eventually, the solid interior takes over most of the star, leaving only thin layers near the surface still fluid. With more time, even those layers freeze, leaving a solid core beneath the light atmosphere of hydrogen or helium that sits at the top. The object is then about as compact as a white dwarf can be without stepping into a different category of matter entirely. How long it takes to reach these stages depends on cooling, and cooling for white dwarfs is slow. The rate at which something radiates energy depends on its temperature and its surface area, a relationship summarized by the Stefan-Boltzmann law. A white dwarf can be very hot, thousands to tens of thousands of degrees, yet it has a small area because it is only Earth-sized. Compared with a normal star like the Sun, the white dwarf's radiating surface is tiny, about a millionth as large. So even at a high temperature, it leaks energy at a modest rate. It is like letting heat out through a pinhole rather than through a wide window. The result is a long, gentle fade that plays out over time, spans beyond human imagination. The oldest white dwarfs we know in the Milky Way are roughly 11 billion years old, nearly as old as the galaxy itself. From their birth temperatures near 100,000 degrees Celsius, they have cooled to around 3,000 degrees, glowing a deep red that is faint even in powerful telescopes. At these temperatures, most of their light shifts out of the visible and into the infrared, so even a nearby old white dwarf is difficult to see. Yet they are still radiating the heat they stored from their formation, and will continue to do so for times that make the current age of the universe look short. Many trillions of years lie ahead for them. The numbers quickly leave everyday experience behind. The coolest white dwarfs that current instruments can detect emit most of their light in the infrared at temperatures near 2,500 degrees. Getting from 100,000 degrees down to that mark takes on the order of 10 billion years. Sliding the last steps from 2,500 degrees to only a few degrees above absolute zero takes far longer, approximately 10 quadrillion years, which is a 1 followed by 16 zeros. That is 1,000,000 billion years. For comparison, the age of the universe today is about 13.8 billion years. The white dwarf's quiet fade outlasts that by a factor of about 1,000,000. Over that span, small effects matter. Crystallization adds pauses. Trace elements in the outer skin change how efficiently light escapes. Even weak magnetic fields and thin layers of hydrogen or helium can tweak the cooling curve. During that huge stretch, the character of the cooling changes. At first, it is relatively fast in cosmic terms. Blue-white becomes white, then yellowish, then red over the first few billion years. Most known white dwarfs sit somewhere in this stage. They are young enough to glow and old enough to be common. After that, the pace slows. Red slides into infrared over tens of billions of years, and bright infrared dims further over hundreds of billions. Around 100 trillion years out, the white dwarf's surface temperature will be so low that its glow blends into the background radiation of the universe, the faint microwave afterglow left from the Big Bang. That background itself cools with time, but the white dwarf is declining even faster, so there is a long stretch where the two are nearly matched. At that point, by our definitions, there is no detectable radiation left to pick out with a telescope. The object crosses an observational line and earns a new label. We would call it a black dwarf. The term can be confusing, so it helps to say what it is not. It is not a black hole, and it does not trap light. Black here simply means too dim to see, an ember that is cooled so far that it no longer stands out against the cosmic background. A black dwarf is a stellar remnant in its quietest state, cold, compact, and dark, the residual matter of a star whose heat has been squandered into space over spans no living creature will witness. The interior is solid, The electrons still provide quantum pressure, and the outermost skin is an ultra-thin layer of the lightest gas left. In that form, a black dwarf can wait for what seems like forever, barely changing except for the drift of the universe around it. None exists today because the universe is not old enough to make even one. The very oldest white dwarfs, born from some of the first stars more than 13 billion years ago, still glow faintly in the infrared and will continue to do so for trillions of years. The first true black dwarf will not form for at least 10 quadrillion years, and likely longer, depending on details like how we define too dim to detect and the exact cooling physics at very low temperatures. The general picture is firm, even if the last decimal places are not. Some models include tiny amounts of energy from very slow nuclear reactions triggered by quantum tunneling. Others include the gradual sinking of heavier atoms in the solid, which can release heat much later than you might expect. These refinements shift the exact timing but do not change the broad path: shine, cool, crystallize, and vanish from view. It helps to anchor these scales with a few simple comparisons. The universe today, 13.8 billion years. The sun's future as a white dwarf begins in roughly 7 billion years. After that, its remnant would need about 10 quadrillion years to fade from a dim infrared spark to an undetectable black dwarf. That span is around 700,000 times the current age of the universe. If you compress all of cosmic history so far into a single second, the white dwarf's path to true darkness would stretch for about 8 days. If the age of the universe were 1 meter on a ruler, the cooling time to a black dwarf would be roughly 700 kilometers. If the universe's age were 1 hour on a clock, the cooling time would run for 80 years. Place those side by side, and a pattern appears. No matter how you scale the story, the cooling takes far longer than anything else we normally measure. Along the way, the surface makeup can keep evolving in quiet ways. Gravity sorts elements by weight, so hydrogen, being the lightest, floats to the top, even if only a paper-thin layer exists. That thin skin can dominate what we see because it blocks and shapes light passing through it. In some white dwarfs, hydrogen is gone or buried, and helium takes over the spectrum. Those become DB types. In others, a recent bite of rocky debris sprinkles the atmosphere with metals like calcium or iron. Those metals sink quickly in the strong gravity, so their presence tells us we caught the star soon after the meal. These details are reminders that even a dead star has a subtle life in its outermost layers, while the interior continues its slow march toward a fully solid state. The internal physics remains steady and simple in principle. Electron degeneracy pressure holds the star up. Temperature does not matter for that support, so cooling does not bring a collapse. Instead, cooling only dims the light. The core hardens, the lattice grows, heat leaks out through a small surface. Bit by bit, the star's glow slips from visible light to red, then to deep infrared, and finally below any band our instruments can pick up. Seen from far away on that last stretch, the white dwarf would not stand out against the darkness at all. It would be a silent mass that still curves space with its gravity yet gives off almost nothing. Because our tools are limited to the present age, we cannot watch a single white dwarf make the whole trip. What we can do is gather many white dwarfs at different stages and line them up like frames in a long time lapse. Star clusters help with this because their stars formed around the same time. In a cluster, The white dwarfs share a common age and distance, so small differences in color and brightness map cleanly to differences in mass and cooling state. That is how the Gaia result was so persuasive. Across huge samples, the small brightening from latent heat showed up as a crowd on the color magnitude diagram, right where crystallization theory said it should be. The observation matched the prediction, which is how astronomy often makes progress when the thing we want to test unfolds over ages we cannot personally see. Put all of this together, and the picture is clear. A white dwarf starts hot, cools, and while cooling, locks its ions into a crystal lattice. The process takes a long time because the object is small in area and big in stored heat. The atmosphere may look different from one star to another, but the deep interior follows the same script. Much later, after countless eras, the star becomes a black dwarf, solid, cold, and invisible, yet still present as mass and memory of a sun that once shone. However you scale the story, the conclusion remains the same. Black dwarfs belong to a future so distant that, next to any human span, it feels like infinity. While a white dwarf is cooling toward that state, the universe around it keeps changing in slow, steady ways. First comes the fate of ordinary stars. The main sequence ends for all of them. The tiniest red dwarfs, which burn their fuel with great care, can shine for trillions of years. They mix their interiors well and waste very little, so they last far longer than stars like the Sunday, yet even they are limited. After enough time, their hydrogen runs low, their cores change, and they fade into white dwarfs. By the time the first true black dwarfs exist, even the last red dwarf will have dimmed long before. The stelliferous era, the age when fusion in stars lights the sky, will have ended. What we think of as the normal night, dotted with stars, will be a memory held only by the oldest remnants. Galaxies will not look the way they do now. Over very long times, stars in a galaxy exchange small kicks of energy when they pass one another, or when they interact with big objects like giant molecular clouds and central black holes. Some stars lose energy and sink inward. Others gain energy and are pushed onto wider orbits. A few are flung free at escape speed and drift into intergalactic space. Close pairs and crowded clusters radiate tiny amounts of energy as gravitational waves when masses move and accelerate. The effect is faint, but eternity is patient. Bit by bit, orbits change. The densest centers feed their supermassive black holes, while the outskirts thin out. Neighboring galaxies that are bound to each other will merge, but later, gravity has less to work with. On the largest scales, groups and clusters that are not tightly bound will disperse as expansion stretches the space between them. The neat ladders of structure we map today, galaxies gathered into clusters and clusters into superclusters, fade into great distances with lonely islands cut off from one another. Planets will not keep their familiar places either. The inner worlds of many systems are at risk much earlier when their stars swell into giants. In our own system, Earth will not survive the sun's red giant phase. Farther out, planets that made it through may not remain where we expect. Over long periods, small gravitational tugs add up. A passing star can disturb a wide orbit. A hidden chain of pushes among several giant planets can knock a smaller world into a new path. Many planets will be ejected as rogues, roaming between stars. Others will drift inward through countless minute interactions and end their journey by merging with their parent white dwarf or by being torn apart into streams of debris. For the sun, what remains after all changes is a white dwarf with a very thin atmosphere and a cloud of cooled relics, or no companions at all. The tidy architecture we study now gives way to a quiet scene with a single faint object gliding through space. The background light of the universe also evolves. Today, the cosmic microwave background, the afterglow of the Big Bang, has a temperature of about 2.7 Kelvin, only a little above absolute zero. As space expands, those photons stretch to longer wavelengths and cool. In 10 quadrillion years, the background temperature drops to less than a millionth of a degree above absolute zero. The sky that once glowed with a gentle microwave hiss becomes almost perfectly cold. That is the stage on which black dwarfs exist. A universe with no fresh fuel for stars, no broad sources of heat, and only relics left over from earlier ages. From a human point of view, it is dark and close to empty, yet it is not without activity. Physics does not retire. Quantum mechanics and gravity continue to operate no matter how slow the changes appear. To make sense of the whole timeline, it helps to break the deep future into broad eras. Cosmologists do this to keep track of which processes matter most at different times. Right now, we live in the Stelliferous era, the age of star formation and starlight. It began when the first stars switched on, roughly 100 million years after the Big Bang, and lasts until the last stars stop fusing hydrogen. The end point sits around 100 trillion years in the future 14 years. By then, even the smallest red dwarfs have burned through their fuel and become white dwarfs. Natural fusion fire goes out. Light from stars ends. Only rare and special cases can still create fusion after that, and we will come back to those. After the Stelliferous era comes the degenerate era, named for the degenerate matter that supports white dwarfs and the related exotic states in neutron stars. This stretch runs from about 14 years to around 40 years. In it, the universe is dominated by remnants, white dwarfs in various stages of cooling, neutron stars that no longer have fusion but still have intense gravity and magnetic fields, and black holes. None of these objects make energy in the simple way stars do. They only store heat from their formation and leak it slowly into space. Early in the degenerate era, white dwarfs cool and crystallize and eventually pass below detectability. We call them black dwarfs once they are too dim to see. The time it takes depends on mass, composition, and small details in the physics of how heat travels through their interiors. Many estimates place the typical cooling to black dwarf time between about 10-15 and 10-30 years. That range is wide, 15 orders of magnitude, which shows both how hard it is to test these models directly and how sensitive the answer can be to assumptions at very low temperatures. Even so, it places the transition far beyond the ages we can probe today. Past that, another question may surface. Do protons last forever? Protons are the building blocks of ordinary atomic nuclei. Some theories that try to join the forces of nature into a single framework, grand unified theories, predict that protons can decay into lighter particles given enough time. Experiments have watched large volumes of material for years and have not seen a decay, which sets a lower bound on the proton lifetime, around 10-34 years. That means that if decay happens, it takes longer than that. Some models suggest lifetimes around 36 to 45 years. If protons are unstable on those scales, then black dwarfs would not remain whole forever. Their nuclei would slowly break apart. The star's matter would change into lighter particles like positrons and photons, and the object would, in a sense, evaporate without heat. If, instead, protons are stable or decay only on times even longer than 1040 to 1045 years, then black dwarfs can persist into later eras largely intact, cooling and changing only by very slow processes. Assuming protons do not spoil the scene too early, the universe eventually enters the black hole era. Here, the most significant power source left is Hawking radiation from black holes. In 1974, Stephen Hawking showed that quantum effects near a black hole's event horizon allow pairs of particles to appear briefly from the vacuum. Usually they meet and annihilate again, but if one falls in and the other escapes, the black hole loses a tiny bit of mass. Over great time, this trickle adds up. The smaller the black hole, the faster it evaporates. The larger the black hole, the slower the process. A black hole with the mass of the sun would take about 1067 years to vanish by Hawking radiation. Supermassive black holes, millions or billions of solar masses, would take about 100 years or even longer to fully evaporate. Compared with those spans, the time for a white dwarf to cool into a black dwarf is quick. Eventually, after the black holes have finished evaporating, the universe would enter what is called the dark era. In this last stage, if protons are stable, the contents are black dwarfs, stray electrons and positrons, neutrinos, and a very dilute bath of low-energy photons. If protons are not stable, then even black dwarfs will have faded into lighter particles by then, leaving almost nothing that can store or release useful energy. The global temperature is as close to absolute zero as any process can make it. Matter and radiation are spread thin by expansion, so collisions are rare. No engines remain that can do work in the thermodynamic sense. This is what people call heat death, not an explosion or a crash, but a slow settling into maximum entropy, where nothing large-scale can change because there are no gradients left to drive it. Nothing is a strong word, though, and the far future still holds quiet processes. Even in the deepest cold, quantum mechanics allows rare events. Inside black dwarfs, given unbelievable amounts of time, tunneling can let nuclei fuse into heavier ones. In some models, that slow drift toward iron is what eventually tips a few massive black dwarfs into collapse and triggers a final supernova. Elsewhere, weak interactions can change particles on enormous timescales. In halos and long streams, gravity still curves space and guides whatever mass remains. The activity is sparse, but it does not stop altogether. The point is not that physics ends. It is that the universe no longer has abundant, quick ways to rearrange energy into vivid forms like starlight. All of these eras ask us to think in numbers that bend the mind, so anchoring them with comparisons can help. The end of the stelliferous era at about 1014 years marks the time when star formation is done and red dwarfs have left the main sequence. The time for many white dwarfs to cool into black dwarfs sits somewhere between 1015 and 1030 years, depending on details. The possible onset of proton decay, if it exists, might matter around 1036 years or later. A solar mass black hole evaporates in roughly 1067 years, while giant ones can take up to 100 years. Each step is not just bigger, it is bigger by factors that erase the scales we live by. Even before black holes dominate, the cooling of the background light sets the scene for black dwarfs. As the cosmic microwave background cools toward a microkelvin and below, the last heat advantages disappear. A black dwarf already faint, becomes effectively invisible. Its light cannot rise above the background unless you are practically on top of it, and even then, there is almost nothing to see. The only clear signal left would be gravity, the way the object bends the path of a passing body or lensing a remote source by a fraction too small to measure with any realistic instrument. In that sense, a black dwarf is present, but hidden, cold, but still massive, like a stone in a perfectly dark room. The uncertainty in the exact timelines is honest. It comes from gaps in data at temperatures and densities we cannot reproduce on Earth, and from the sheer length of the processes. Cooling depends on the star's mass, the thickness and composition of its surface layers, the details of crystallization and phase separation, and small effects like magnetic fields. Proton decay depends on high-energy physics we have not yet pinned down. The long tail of Hawking radiation depends on quantum gravity in a regime that remains hard to test. Yet the broad outline has strong support because many pieces line up. We have white dwarfs at many stages to chart the early cooling. We have theory that matches their behavior. And we have firm mathematics describing how black holes lose mass with time. The distant digits may move, but the shape of the curve stays. For a sense of scale that connects back to everyday time, consider again the age of the universe now, about 13.8 billion years. The time for a typical white dwarf to cross the threshold into a black dwarf ranges from 10, 15 to 10-30 years in many models. That is longer than today's age by factors from 100,000 up to 1 trillion. If you mapped the current age of the universe to a single second, the delay before black dwarfs appear would span anywhere from 3 years to 30 billion years, depending on which estimate you choose. The time for protons to decay, if they decay at all, sits even farther out on the timeline. A lifetime of 36 years is about 10 trillion times longer than the universe has existed so far. If you shrink the current age of the universe to a single second, a 36-year event would land 300 trillion years away on that scale. That is roughly 20,000 times longer than the whole history we compressed into that 1 second. Push the comparison again, and the next landmark, the evaporation of the largest black holes, breaks every tool we use to make sense of time. The lifetime for a supermassive black hole can reach about 100 years. That number is called a googol, a 1 followed by 100 zeros. It exceeds the present age of the universe by a factor on the order of 1090. There is no everyday picture that makes a span like that feel familiar. It is simply beyond intuition. What matters for our story is this: black dwarfs, while staggeringly ancient, arrive early compared with black hole evaporation. By the time the universe is roughly 30 years old, and certainly by 40 years, most ordinary white dwarfs will have cooled below any detectable glow and will count as black dwarfs if protons have not undermined them by decaying first. In that deep future, these objects become the dominant form of normal matter. They drift alone over distances so wide that almost none will meet another again. Their surfaces will settle at temperatures less than a degree above absolute zero. They will not shine at any wavelength we can name. They will be invisible to any telescope we can imagine. They will be the forgotten leftovers of stars that ended so long ago that even the last traces of their heat have seeped into space. Yet the words inert and finished do not quite apply. Deep in the cores of black dwarfs, a slow, strange process continues. It is quiet enough to leave no light and steady enough to remake the interior over spans that make even 10, 40 years look small. The key is quantum tunneling, one of the most counterintuitive ideas in physics. Tunneling lets particles cross energy barriers that classical rules say they cannot cross. It is why some atomic nuclei spit out particles and decay. It is part of how electrons move in devices so small that waves, not dots, describe them. It is also the reason fusion can occur in stars like our sun, at temperatures lower than a simple ball rolling over a hill picture would suggest. A quick picture helps. In classical physics, a particle needs enough energy to climb over a barrier. Imagine a ball rolling toward a hill. If the ball does not have enough speed to reach the top, it rolls back. To get to the other side, you must give it more energy. Quantum mechanics changes the story because particles are not just points with exact positions and speeds. They are described by wave functions, which tell you the chance of finding them here or there. These wave functions can spread into a barrier instead of stopping at a sharp edge. That spread means there is a small, non-zero chance that a particle appears on the far side without ever going over the top in the classical sense. The chance falls off rapidly as the barrier gets higher or wider, but it does not drop to zero. And when time is nearly unbounded, small chances can win. A black dwarf's interior gives tunneling a playground. Inside, the nuclei sit in a crystalline lattice. The temperature is only fractions of a degree above absolute zero, so the ions barely vibrate around fixed locations. Each nucleus carries positive charge, so there is an electrostatic barrier between any two of them. To fuse, two nuclei must get so close that the strong nuclear force can grab them and glue them together. In a live star, heat gives the nuclei enough kinetic energy to approach that close, and tunneling helps them cross the last part of the barrier. In the sun's core, at about 15 million degrees Celsius, hydrogen nuclei fuse by tunneling through the tail end of their electromagnetic barrier to become helium. That is the path to sunshine. In a black dwarf, there is no heat to help. The ions are cold and still. Classical physics would say fusion is over forever. Quantum mechanics leaves a loophole. Even with almost no thermal motion, a tiny fraction of nuclei will, now and then, tunnel through the entire barrier and meet. The probability for any one pair is unbelievably small, and the time you would have to wait for a single event in a single region is unbelievably long. But a black dwarf is full of nuclei, and the universe gives them time. Over enough years, so many, that we need new words. Fusion events happen. Each event releases a bit of energy, but not enough to warm the star. Whatever heat appears radiates away into almost zero surroundings, keeping the black dwarf at nearly the same temperature as the background. Physicists Fred Adams and Gregory Laughlin examined this idea in detail. They calculated how tunneling-driven fusion proceeds in compact remnants across huge spans of time. Their results say something that feels almost like a paradox. Even in the coldest possible future, fusion can continue at a rate so slow it looks motionless, converting lighter nuclei into heavier ones step by step. The timescales they discuss run to about 10, 1,000, 500 years for bulk changes in composition. Yes, 10 to the 1500th power. That number does not fit inside the head. It does not need to. The point is that the process, while slower than anything familiar, keeps going as long as there are nuclei to rearrange. The path begins with the stuff most white dwarfs are made of: carbon and oxygen. Those elements formed when the parent stars ended their fusion lives and shed their outer layers. In the black dwarf, Tunneling lets pairs of carbon nuclei meet, and pairs of oxygen nuclei meet, and mixtures of carbon and oxygen meet. The products are heavier nuclei that sit a little lower on the curve of nuclear binding energy. That phrase means they are more tightly bound, so fusing them releases a tiny surplus of energy, just enough to keep the tally going as heat flows away. The first stops on this slow climb are elements like neon and magnesium. Reactions can take many paths. Carbon plus carbon can become neon, or sodium plus something else. Oxygen plus oxygen can lead to silicon or sulfur. Oxygen plus carbon can split the difference and build intermediate steps. Every path involves tunneling through a barrier taller than any everyday process, but every path also has a chance, and time makes chances add up. As the composition changes, the interior structure adjusts in small ways. Heavier nuclei tend to sink a bit in the solid lattice, just as heavier elements settle in the liquid phase during earlier crystallization. That sinking can release potential energy, which again leaks away as faint heat. The lattice itself can affect reaction rates by placing nuclei at known distances and by setting the vibration patterns, the phonons that shake the positions just enough to test the barrier. Strong magnetic fields, if any remain from the white dwarf's earlier life, can guide electrons and change how heat moves, but they do not stop the fundamental tunneling. The electron sea that provides degeneracy pressure is still there, holding gravity at bay. Temperature does not hold up the star, so cooling cannot collapse it. The only things that change are which nuclei sit where and which ones are left to react. The reaction chain is not a single straight line. It is a web. Carbon can find carbon or oxygen. Oxygen can find oxygen or neon that formed earlier. Neon can later meet magnesium. Magnesium can meet silicon. And each of those interactions can make a new nucleus and a spare particle, or a gamma-ray photon, that carries off a little energy. The black dwarf does not warm. It does not glow. It just trades one arrangement of nuclei for another, always drifting toward more stable combinations. The direction is set by nuclear binding energy. Moving from lighter to heavier up to a special point releases energy, and moving beyond that requires energy. That special point is iron. In nuclear physics, iron and nearby elements like nickel sit at the peak of binding energy per nucleon. Fusing lighter elements up to iron releases energy. Trying to fuse iron into heavier elements eats energy. That is why ordinary stars cannot power themselves by fusing iron. Once a core is rich in iron, more fusion does not help the pressure problem. It makes it worse. In explosive events like core collapse supernovas, iron is the sign that normal fusion has reached the end of the road. In a black dwarf, the story is not explosive, at least not yet in the part we are describing, but the sign is the same. The slow, tunneling-driven buildup of heavier and heavier nuclei eventually pushes the composition toward iron and its neighbors. The times involved are so long that even calling them long feels like a joke. For perspective, returning to numbers, if it takes around 10, 15 to 10, 30 years for typical white dwarfs to cool into black dwarfs, that is already longer than the current age of the universe by factors from 100,000 to a trillion. If proton decay waits until 10, 36 years or more, then black dwarfs have eons to sit and change. The Hawking evaporation of even a solar mass black hole is 67 years. The giants in galactic cores can take up to 100 years. Next to those numbers, 10, 1,000, 500 makes everything else look recent. You can try analogies, compress the age of the universe to a second, stretch it to a day, a year, a lifetime, and they fall apart before reaching 10, 1000, 500. The point is not to pin down the exact date. The point is to see that, given the only resource the far future has in abundance, time, these rare reactions cannot be ignored. The environment inside the black dwarf also keeps the lanes open. Because the ions sit in a crystal lattice, their positions are not random. That order means the distance to tunnel is set by the geometry of the lattice and by the small vibrations about each site. Those vibrations never vanish entirely, even near absolute zero, because of quantum zero-point motion. The stillness helps and hinders at once. There are no hot collisions to help, but the barriers are sharply defined and can be crossed by pure tunneling. Electrons, meanwhile, fill up their allowed states as before, keeping the degeneracy pressure that supports the mass. Neutrinos, those nearly massless particles made in some reactions, fly out without interacting. Photons, born in the reactions, take a long way out through the dense material but eventually escape, carrying away any slight energy surplus so the temperature remains tied to the background. As tunneling proceeds over unspeakable ages, the menu of reactions shrinks. The easiest light pairs have largely combined. The stock of intermediate elements like neon and magnesium grows. Then they too meet partners and step onward. Silicon appears and later feeds reactions of its own. Branches of the web close as the mix concentrates in nuclei that are closer to the iron peak. The energy released at each step keeps dropping as you move up the binding curve. The black dwarf remains cold and silent. The only signs of change are on paper, slowly varying ratios of elements that no instrument could measure in such a dark world. It helps to stress what does not happen in this stage. There's no runaway heat. There is no new source of pressure to puff up the star. There is no bright burst of radiation that would give away the location. The quantum mechanical leak through the barrier is the entire engine, and it is as gentle as physics can make it. It is also relentless. The longer you wait, the more reactions you collect. The longer you wait, the heavier the average nucleus becomes. The longer you wait, the closer the mixture drifts to iron. Even the uncertainties in physics do not change this direction. If protons decay on times shorter than the longest tunneling times, the black dwarf's matter will thin out and fade in a different way. If protons are stable for times longer than 10, 45 years, the tunneling track continues without interruption. If subtle effects in the lattice tilt certain reaction rates up or down, the schedule changes, but the destination does not. Gravity keeps the mass compressed. Degeneracy keeps it supported. Cooling keeps the temperature pinned near the background. Quantum rules keep the door to fusion cracked open. Given spans that have room for 10, 1,000, 500 years, rare becomes expected. All these threads bring the composition to the same place, piece by piece, through a chain of ultra-slow fusions. The black dwarf shifts from a carbon-oxygen crystal to a mixture richer in neon and magnesium, then in silicon and its neighbors, and finally in iron group nuclei. The reactions that add to iron still release a little energy. The reactions that try to go beyond iron would need to consume energy instead. There is no budget for that in a world that cold. So the nuclear chemistry of the core funnels toward iron as an endpoint. In a black dwarf, the slow accumulation of iron through quantum tunneling fusion represents the end of the line. Once nuclei settle into iron, the path forward closes. Pushing past iron would require an input of energy, and a black dwarf has no heat source to supply it. So iron builds up in the core, grain by grain on timescales that bury every other number we have used. The accumulation is slow, but it is relentless, and it sets the stage for an outcome that is anything but quiet. There is a mass threshold that governs compact stars, the Chandrasekhar limit, named for Subramanian Chandrasekhar, who worked out its physics in the early 1930 seconds. The value is about 1.4 times the mass of the Sunday. Below that mass, electron degeneracy pressure can hold gravity in check. Above it, electrons alone cannot provide enough support, and collapse follows unless some other form of pressure intervenes. In the familiar universe, white dwarfs can be pushed toward this limit by taking on matter from a companion star. As the mass creeps higher, the star becomes unstable. Gravity squeezes harder, the internal density rises, and temperature climbs. Runaway fusion of carbon and oxygen begins and races through the star, unbinding it in a thermonuclear blast. That is the Type Ia supernova, one of the brightest lights the cosmos makes, bright enough to rival a whole galaxy for a short time. Because these explosions reach similar peak luminosities, astronomers have used them as standard candles to measure the expansion of the universe. Now, imagine an echo of that mechanism without the heat. A black dwarf that has spent unthinkable ages slowly transmuting its inner material by quantum tunneling ends up with an iron-rich core. It does not accrete fresh gas from a companion. The universe is far past the era when close binaries feed one another. Instead, the internal chemistry drifts toward heavier nuclei until a critical fraction of the mass is iron, and the total mass sits near the same Chandrasekhar threshold. At that point, with too much weight pressing inward and too little electron pressure left to resist, collapse begins. The early collapse is cold. Without thermal energy to cushion it, the matter contracts under gravity and forces electrons into ever higher momentum states. As the density rises, the energy of those electrons grows so large that a new channel opens. Electrons are captured by protons inside nuclei, turning protons into neutrons and releasing neutrinos that escape freely. This electron capture, often called neutronization, removes the very electrons whose degeneracy pressure was holding the star up. With that support gone, the collapse accelerates. An object the size of Earth plunges toward nuclear densities in a slice of a second. The rush inward releases a huge amount of gravitational potential energy. Some of that energy goes into breaking apart iron group nuclei, a process called photodisintegration if high-energy photons are involved, or more generally dissociation, and then rearranging the pieces. The matter rebounds, where the core stiffens at near nuclear density, and a shock forms. What follows is a detonation that rips through the body of the black dwarf. This is the black dwarf supernova, often described as an iron supernova, because the dominant fuel is iron rather than carbon and oxygen. The trigger resembles a Type Ia in the sense that a degenerate core exceeds a limiting mass and can no longer be supported. But the details differ because the composition and thermal state are different. The differences matter for what we would see if we existed to see it. A Type Ia is powered by thermonuclear burning of carbon and oxygen into nickel and iron, which releases large amounts of energy and synthesizes copious radioactive nickel 5-6 that powers a bright light curve. In contrast, a black dwarf supernova starts from iron, already close to the most tightly bound state. Breaking iron and reassembling it does not yield as big an energy surplus. The result should be dimmer, perhaps 100th to 1,000th the peak brightness of a classic Type Ia. It would still be luminous on an absolute scale, a sharp spike of light and neutrinos against a black sky, but not the galaxy outshining beacon we associate with younger cosmic times. In a universe that has been dark for 10, 40 years or more, any explosion at all is dramatic. For hours or days, a small region would flicker with photons born in the shock and in the radioactive decays of freshly made isotopes. Neutrinos would stream out almost unimpeded. A passing observer would not exist, but the signals would be real. Packets of energy racing outward at light speed, imprinted with the physics of a collapse that began without heat. Then the glare would fade. The debris would spread, thin, and cool into the already cold background. The remnant matter would join the dilute fog of particles and radiation that fills space in the late universe. The concept rests on a handful of questions we can state cleanly, even if their answers involve extreme extrapolation. How long does it take quantum tunneling to turn a carbon-oxygen crystal into iron in a star-sized block of degenerate matter? How close must the total mass be to the Chandrasekhar limit for collapse to be triggered once electron captures begin in earnest? How does the solid lattice, the distribution of elements, and the weak, lingering temperature of the environment tweak those thresholds? Because we cannot experiment on objects that live for 10, 100 years. The uncertainties are large. Yet, within the broad assumptions, the logic points to an outcome that is hard to avoid. If protons are stable for sufficiently long times, if tunneling continues at even feeble rates, and if gravity has its usual strength, then some fraction of massive black dwarfs will eventually reach the conditions for collapse. Estimates for when the first of these events could occur vary widely. Fred Adams and Gregory Laughlin analyzed tunneling-driven fusion in stellar remnants and argued that the timescales are so immense that they make nearly every other cosmic process look quick. Using their framework, and in later work that refines the reaction paths and rates, a representative figure for the onset of black dwarf supernovas is around 10, 1,000, 100 years into the future. Other authors, working with more conservative assumptions about tunneling probabilities and lattice effects, push the start much later numbers, like 10, 3, 2, 0, 0, 0 years, appear in the literature as thought experiments rather than precise predictions. The difference spans thousands of orders of magnitude, which underscores how sensitive the calculation is to nuclear details at temperatures we will never recreate. But for the narrative at hand, the exact exponent is not the point. What matters is that the time is so large that it dwarfs even black hole evaporation, and yet it is still finite. Take 10, 1,000, 100 years as a stand-in. It is a 1 followed by 1,100 zeros, a figure that does not fit on a page. It exceeds the current age of the universe by a factor of roughly 10, 1,090. If you replace the 13.8 billion years we know with the shortest meaningful tick in physics, the Planck time, and then stacked those ticks into years, you would still be nowhere close. Analogies fail because our scales are built for lives, histories, and geologies, not for the endurance of degenerate stars drifting through an empty cosmos. The lesson to keep is modest. Given enough time, even impossible reactions proceed, and their aggregate effect can push a compact remnant over a threshold set by gravity and quantum rules. The explosion's energetics follow from composition. Iron group material is hard to burn. It sits at the top of the binding energy curve. The shock that forms at core bounce must do more unbinding and less nuclear fueling than in a hot, carbon-rich white dwarf. Less radioactive nickel is synthesized, so the light curve tops out at a dimmer peak and decays faster. Neutrinos likely carry away a large fraction of the energy, as in other core collapse scenarios. But here the starting point is cold, so the thermal neutrino pulse associated with an initially hot core is muted. The ejecta would be rich in iron group and perhaps some intermediate mass elements formed in the shock, without surrounding gas or dust in any meaningful quantity. There would be little for the ejecta to crash into, so late-time emission powered by shocks would be modest. Every trait points to a brief flare in a universe that otherwise emits none. The aftermath is simple. The black dwarf is gone, replaced by an expanding, ever-thinning shell of nuclei and free particles. There is no nearby gas to capture the debris. There is no galactic magnetic field to trap charged particles for long. The material becomes part of the interstitial background, another contribution to entropy in a cosmos that has long since reached its thermodynamic limits. If the collapsing core overshot into neutron star densities before the shock unbound the star, a small, inert neutron star might remain. If the mass were high enough, a direct collapse to a tiny black hole could occur, though the initial assumptions behind the iron supernova picture usually place the mass near the Chandrasekhar value, favoring total disruption. In any case, what matters for the energy budget is that a compact, cold object stores gravitational potential. When the support fails, that storehouse can be tapped one last time. Cosmic expansion shapes what these flashes can influence. The universe does not pause while black dwarfs wait. It keeps stretching. Structures that are not gravitationally bound drift apart, then lose contact with one another. By the era of black dwarf supernovas, typical separations between remnants will be measured first in light years, then in millions, then in billions, and eventually in numbers that make even trillion feel small. Each remnant sits alone in its own expanding region. When an explosion occurs, its photons stream outward at the speed of light, but space between everything is also growing. The wavelengths stretch cosmological redshift, so the photons slide down the spectrum into longer and longer wavelengths. Over enough time, a single photon can be redshifted so far that, measured in the units natural to the moment, its wavelength exceeds any bounded scale you could call an observable universe for that isolated region. The energy is not lost in a bookkeeping sense, but it is diluted and softened past practical detection. That leads to a natural question often asked in quieter contexts. If an event happens with no observers, what is its standing? The late universe offers a crisp version of this puzzle. A black dwarf supernova produces light, neutrinos, and a whisper of gravitational waves. Those signals travel outward, but they do not meet instruments, planets, or eyes. There are no civilizations left to build telescopes, no archives to store observations, no languages to name what occurred. The signals still move. The ejecta still expands. The conservation laws still balance the books. In this sense, the event is complete whether or not it is recorded, and yet the explosions will happen. The laws of physics do not ask for witnesses. Whether anyone is there to measure them or not, quantum tunneling will go on. Iron will build up. Some black dwarfs will cross the Chandrasekhar limit. When they do, they will explode. The universe will produce those events as surely as a wound spring lets go when you lift your thumb, even if no one is present to hear the snap or see the brief light. But not every black dwarf is a candidate. Mass is the key. Only remnants whose masses lie near the Chandrasekhar threshold have any realistic chance to become supernovas. Most are simply too light. A typical sun-like star leaves behind a white dwarf of about 0.6 solar masses, roughly 60% of the sun's mass. That sits far below the roughly 1.4 solar mass limit where electron degeneracy pressure fails. Cooling into a black dwarf and then slowly converting carbon and oxygen into heavier elements by tunneling does not add mass. It only changes the mix. No matter how long you wait, that remnant will never reach the critical mass needed for collapse. The sun's descendant will harden into a cold, dark, crystallized object and, over ages beyond imagination, drift toward an iron-rich composition. If protons decay on very long timescales, that decay will eventually erase even the atoms. If protons are stable, the remnant will persist as a silent, iron-laced stone in space. Most stars end their lives with remnants between about 0.5 and 0.9 solar masses. That covers the majority of white dwarfs. These will cool, crystallize, and given enough time, quietly transmute much of their interiors into iron through tunneling. But they will never become heavy enough to collapse. They are eternal in practice. A smaller group begins life with more mass and loses less of it during the giant phases. Stars born in the range of roughly 6 to 8 times the mass of the sun often leave white dwarfs close to 1.1, 1.2, or even 1.3 solar masses. These are the interesting cases. They do not collapse immediately because electrons still provide enough pressure, yet they sit near the cliff. If their cores later become iron-rich, and if subtle changes reduce electron pressure through electron captures, for example, the balance can tip. These are the black dwarfs with a non-zero chance of a future supernova. How many fall into that set depends on the birth masses of stars and on how much mass those stars shed late in life. The initial mass function tells us that low-mass stars are common and high-mass stars are rare, so the number of near-limit white dwarfs is small compared with the total. Even so, small can be a lot. If only 1 to 10% of all black dwarfs eventually reach conditions for collapse, that small fraction becomes a huge absolute count in a universe that began with vast numbers of stars. The Milky Way alone likely formed on the order of a few 100 billion stars. Over the next 100 trillion years of ordinary stellar evolution, most of those will end as white dwarfs and then continue cooling. If 1% of the final black dwarfs in our galaxy-sized family tree ultimately explode, that would be around 2 billion black dwarf supernovas linked to the material that once made the Milky Way. The observable universe holds well over 1 trillion galaxies. Multiplying a modest fraction by an enormous base gives a total number of explosions that could reach 10, 21, or more. The catch is that observable universe stops being a useful phrase at those times. Structures have merged, thinned, or separated beyond contact. The count is an accounting exercise, not a practical catalog. By the era when any of this happens, familiar names like galaxy, spiral arm, and star cluster have lost their grounding. The Milky Way and Andromeda will have merged long before, forming a massive system whose stars then scatter through interactions over longer spans. Many fall inward to feed the central black hole. Many more are tossed outward into space. Bound groups evaporate one slow encounter at a time. After even longer delays, nothing like a galaxy remains, only isolated remnants separated by wide, growing gaps. Still, the explosions will occur. They will blink on here and there, each isolated in its own quiet region, and then vanish. You can map this onto specific nearby examples to ground the idea. Sirius A, a bright, young, hot star about twice the mass of the Sun, will end as a white dwarf near 1 solar mass. That is still far from the 1.4 solar mass threshold, so its black dwarf descendant will never cross the line by tunneling alone. Sirius B, already a white dwarf of about a solar mass, faces the same limit. It will cool, crystallize, and age without a final blast. Procyon A, with a mass around 1.5 solar masses, should leave a white dwarf of roughly 0.6, 0.7 solar masses, again too light. Procyon B, already a white dwarf at about 0.6 solar masses, is also too light to ever become unstable. To find viable seeds for far future iron supernovas, you look to systems with higher initial masses that still avoid core collapse in their youth. A star like Vega, around 2.1 solar masses, likely leaves a white dwarf of around 0.91 solar masses, probably still below the interesting range. In more complex systems, tight binaries or triples with initial masses in the middle-high range, or pairs like the 2 stars in Spica, often called Alpha Virginis, which are massive enough to evolve into compact remnants under the right mass loss histories. The outcome depends on details. If the stars explode as core collapse supernovas first, they will not make heavy white dwarfs at all. If they shed enough mass to avoid that fate, they might produce white dwarfs at 1.2, 1.3 solar masses. Those would be candidates, though even then the later pathway depends on composition and on how the lattice and weak interactions change the support as the core drifts toward iron. Part of the challenge is that we cannot predict a single star's white dwarf mass from birth mass with perfect accuracy. The mapping depends on mass loss during giant phases, which depends on winds, spin, magnetic fields, and metallicity, the fraction of elements heavier than helium. 2 stars born with similar masses can lose different amounts and leave different cores. The close passages of companion stars, if any, can also strip or add material. So, rather than point to a specific star today and declare its ultimate fate in the black dwarf epoch, we talk in terms of likelihoods. White dwarfs above about 1.2 solar masses stand out as the more probable precursors. They sit near the limit, and the margin for further change is thin. They need only small shifts in electron pressure or composition to slip past the support line. If tunneling slowly rebuilds the core into iron group nuclei, the stage is set. The steps are steady, even if the calendar is obscene. First, a white dwarf of about 1.2, 1.3 solar masses cools for a very long time. Something between 10, 15, and 10, 30 years to become a black dwarf, depending on its exact mass, atmospheric skin, and how crystallization and phase separation proceed. Then, over periods many orders of magnitude longer, quantum tunneling allows pairs and groups of nuclei to fuse through the Coulomb barrier, crawling up the binding energy curve from carbon and oxygen to neon and magnesium, then to silicon and its neighbors, and finally, toward iron group elements. Throughout, the object remains supported by electron degeneracy pressure and stays cold, radiating away any tiny heat from reactions. Gravity remains patient. When iron dominates and the mass lies close to the Chandrasekhar limit, say around 1.38 solar masses, The old support mechanism starts to falter in the densest zones. At high density, electron capture becomes favorable. Electrons are swallowed by protons in nuclei, creating neutrons and emitting neutrinos. This process removes electrons from the gas that provides degeneracy pressure. Each capture is a tiny step, but in a runaway, each step increases the density and makes more captures possible. The pressure drops faster than gravity can be resisted. Collapse accelerates. In theory, neutronization could begin before iron fully dominates if densities in parts of the core rise high enough. The broad picture is the same either way. Once the support fails, there is no slow landing. The black dwarf implodes. The core stiffens near nuclear density, and a shock forms that runs outward. The details of the explosion differ from a type IA, because iron is the starting point. There is little energy to gain from further fusion. Energy instead comes from the release of gravitational binding as the core collapses and rebounds, and from dissociation and recombination of nuclei under extreme conditions. Less radioactive nickel is created, so the light curve peaks lower and fades faster. Neutrinos likely carry away a large fraction of the energy. The ejecta composition would be heavy in iron group elements, with some intermediate mass products made in the shock. Without a thick interstellar medium, there is not much material to plow into, so later interactions are modest. In absolute terms, the blast is still large, but compared to the brilliant thermonuclear supernovas of the Stelliferous era, it is faint 100th to 1,000th the brightness at peak by many estimates. Spacing in the late universe means each event is on its own. Black dwarfs will be separated by light years, then by millions and billions of light years, and later by distances that defy naming. Expansion stretches space, redshift stretches light. A photon launched from an iron supernova races outward at light speed, but its wavelength lengthens with the fabric of space. Given enough expansion, those photons are dragged to wavelengths so long that, for any practical bounded region, they carry no usable information. The energy is diluted into an ocean that no detector samples. The event still occurred. The conservation laws are satisfied. The debris still expands. The neutrinos still fly. There is simply no audience. Even so, the statistics add up. If 1% of the Milky Way's eventual black dwarf population explodes, you get billions of events tied to our local history alone. Scale that by the original population of galaxies in the observable universe, and you arrive at counts near 10, 21. The number is not a schedule you could put on a calendar. It is a measure of how many separate acts take place over a canvas so wide that no two need be near each other in space or time. The intervals between events in any given region will be enormous. The universe will experience solitary flashes spread across stretches of emptiness and duration. Each is a momentary reversal of a very long trend, a spike of order and brightness in a sea of dark. Return to individual cases for a clearer picture. A star like Sirius A ends too light to matter here. Sirius B is already too light. Procyon A and B both leave remnants that are too light. Vega likely falls short as well. In contrast, systems that start at higher mass but manage to avoid core collapse by losing mass at the right times and rates can end with heavy white dwarfs near 1.2, 1.3 solar masses. In some binaries, where mass transfer is strong in youth, the primary might be stripped enough to miss a core collapse supernova and instead leave a very heavy white dwarf. The secondary might do something similar. Those descendants are the prime candidates. Even then, The final push is not added mass but lost pressure. Tunneling builds iron. Electron captures remove electrons. Degeneracy pressure drops. Gravity wins. There is an important subtlety. Fusion adding mass is not the mechanism. Tunneling rearranges nuclei into tighter bound forms and can change how tightly matter packs. But the star's total mass stays almost the same aside from tiny losses as neutrinos and photons escape. What changes is the equation of state, the relationship between pressure and density, and the availability of electrons to provide pressure. As iron builds and captures proceed, the effective support weakens. You can imagine the star sliding along a stability curve until it crosses the tipping point. At that crossing, the implosion is not a choice. It is a requirement of the physics. After the blast, the result depends on the mass that actually took part and on how the shock behaved. If the star sat very near the Chandrasekhar limit and the shock cleanly unbound it, no compact object remains, only a shell that thins forever. If part of the core reached neutron star density and remained bound before the ejecta escaped, a tiny, cold neutron star might persist. If the mass were somehow above the limit by more than a sliver, a small black hole could form. In the classic picture for iron supernovas from black dwarfs, total disruption is common because the initial mass is near the threshold. Either way, the region returns to near darkness almost at once. The ejecta cools. The particles separate. If protons decay on very long scales, the nuclei will eventually break apart. If protons are stable, the iron group atoms and lighter remnants will wander through space as single atoms or small ions, separated by distances so vast that they rarely, if ever, meet again, and then nothing. The region where a black dwarf supernova occurs settles back into cold and silence. The glow fades, the shock front thins, and the space looks much as it did before low-density particles drifting in a near-perfect dark. The event was brief, but it was real. Its photons and neutrinos carried information outward. Its ejecta added a trace to the background. With that interruption finished, the timeline moves on to what follows after the final possible explosions. This is the last stage, the point at which no process remains that can release large amounts of energy in a single place. Cosmologists call this state true heat death, a condition of maximum entropy where useful differences, temperature gradients, pressure gradients, chemical gradients are gone. Assuming protons are stable on all relevant timescales, the contents are simple to list, even if they are hard to picture. There are black dwarfs that never had enough mass to collapse, plus the remnants of those that did and were not completely disrupted. There are neutron stars here and there, formed in earlier eras or left behind if a collapse outran the shock in a late iron event. There are black holes of many sizes, from stellar mass to supermassive. The rest is a very thin gas of photons, neutrinos, electrons, positrons, if they survive, and a sprinkling of other long-lived particles. The temperature is as close to absolute zero as quantum mechanics allows. The mean density is so low that you could travel for distances measured in trillions of light years and expect to meet no atom at all. In this inventory, black holes stand out as the last engines. They do not explode like stars. They fade. The fading follows Hawking's insight that black holes radiate. Quantum fields near the event horizon allow pairs of particles to appear briefly. If one falls in while the other escapes, the black hole loses a tiny amount of mass. The radiation looks thermal, with a temperature that is inversely proportional to the mass. Large black holes are cold, small ones are warmer. A black hole with the mass of the sun has a temperature on the order of a few dozen nanokelvin, tens of billionths of a degree above absolute zero. Supermassive black holes are even colder, at levels that sit far below any ambient background we experience today. Right now, the cosmic microwave background sets a floor. Its temperature, near 2.7 Kelvin, is vastly higher than any black hole's Hawking temperature. So black holes today gain more from their environment than they lose through radiation. But expansion cools the background. As space stretches, the microwave photons lose energy and the universal bath chills. Calculations place the crossover when the background falls below the temperature of even the largest long-lived black holes, roughly around 10-20 years, give or take the details of expansion. After that, black holes cannot make up the difference by absorbing ambient radiation. Evaporation is no longer hidden. It becomes the dominant trend. The way it unfolds is straightforward and regular. As a black hole radiates, it loses mass. As it loses mass, its temperature rises. The hotter it gets, the faster it radiates. The faster it radiates, the quicker it loses mass. The loop feeds itself, so the final phases speed up. The entire process is slow on human scales. A solar mass black hole needs about 1067 years to evaporate completely. A million solar mass hole requires around 1085 years. A billion solar mass hole takes around 1098 years. These figures are estimates based on semi-classical physics, but are stable enough to draw the picture, compared with the time for black dwarfs to cool and, in rare cases, explode. Black hole evaporation occupies a later, much longer chapter. The endgame for a single black hole looks like a long, quiet fade followed by a brief spike. Most of the time passes with the black hole cold and slowly shrinking. In the final sliver, when the mass gets small, the temperature rises sharply. The radiation spectrum shifts to higher energies. The power output climbs, and the hole releases its remaining mass energy rapidly. You could describe this last instant as explosive, but the total energy is set by E equals mc2, and the schedule is set by the whole evaporation history. For a solar mass black hole, the total energy is about 1047 joules, spread across 1067 years. The average power is tiny, so small that it would be far less than the heat a person radiates today. The final flicker is brief, but it does not compete with a supernova's peak brightness spread over days. It is a last pulse in a very cold universe. While black holes fade, nothing else in bulk generates work. Black dwarf cores have long since finished their tunneling-driven rearrangements or have exploded and dispersed. Neutron stars cool and then sit. Photons, neutrinos, and leptons drift apart as expansion draws all free particles into lower densities. If protons are stable, ordinary matter persists as isolated atoms or ions, but collisions become rare. If protons eventually decay on huge timescales, even those atoms will break down into lighter particles, on schedules that make every other number used here look small. In either case, the overall progression trends toward a thinner and colder state. This is what maximum entropy means in practice. There are no sharp differences left that could fuel engines or stars. There is no gradient to exploit. In a setting like that, one might want to declare that nothing at all happens. That would be close to the truth for any process that needs a sustained energy source. But quantum mechanics leaves room for more subtle possibilities. Even a system at its ground state participates in fluctuations. Fields in vacuum are not rigidly zero everywhere. They have allowed jitters consistent with the uncertainty principle. Most of the time, those jitters cancel, leaving no lasting trace. Very rarely, they can produce transient particles that appear and then vanish. An extreme version of this idea, used as a thought experiment rather than a prediction, asks whether a fluctuation could assemble something complex by chance. In the literature, the example is a Boltzmann brain, named as a nod to Ludwig Boltzmann's work on statistical mechanics. The idea imagines a self-aware structure that momentarily forms out of noise, complete with memories and a sense of self. The odds against such a structure are overwhelming. The probability of arranging so many degrees of freedom in just the right way falls like a double exponential function in the size of the system. People sometimes quote times like 10, 50 years as a scale for such events, not because we expect them, but to point out how far beyond reach they are. These numbers do not fit on a page. The exponents themselves have exponents. Even calling them timescales feels off, since at those levels, the definitions that tie time to measurable change begin to fray. Whether a Boltzmann brain is a coherent concept, whether consciousness could arise in a thermal fluctuation in a way that deserves the name, is not a settled question. The idea sits at the edge between physics and philosophy, used to test the consistency of cosmological models and the meanings we assign to probability and observation. A related speculative line asks whether the vacuum itself is truly stable. Quantum field theory allows the possibility that what we call the vacuum is a metastable state, stable for a long time, but not the lowest possible energy. If so, tunneling could, in principle, nucleate a bubble of a lower energy vacuum. The bubble would expand at near light speed, changing the laws of physics inside it as it goes. In some versions of this idea, the new vacuum might support a different set of particles and forces. In others, the constants we measure would take new values. In either case, our current structures would not survive the transition, but a new region could begin a fresh history with its own conditions. Take that one step further, and you arrive at the baby universe picture. Parts of an inflating space spawn new regions that evolve independently, each with its own properties. None of that is confirmed. We do not have experiments that probe vacuum stability on cosmological scales, and we do not have a complete quantum theory of gravity that would settle what happens at event horizons or at the end of evaporation. These topics live at the edge of current knowledge. They are reasonable extrapolations of known equations into regimes that we cannot access, and as such, they are useful to explore as ways to test internal consistency. But they remain conjectures. The piece we can state without stepping into that zone is the thermal history. Expansion cools the background. Compact objects fade. Black holes evaporate. Free particles spread out. Gradients disappear. You can follow the black hole story with a little more detail to see how it shapes the late environment. When the cosmic microwave background temperature falls below a black hole's Hawking temperature, the hole's net energy balance tilts toward loss. The luminosity of Hawking radiation scales inversely with the square of the mass, so the smallest long-lived holes dominate the energy output at late times. Early on, even they are so cold that their radiation is negligible compared to any ambient glow. Later, once the background fades away, they become the only steady sources. The spectrum is broad and thermal. At large mass, it sits deep in the radio. At small mass, it climbs through microwaves and infrared, then optical and ultraviolet, and into X-rays and gamma rays near the end. Charged particles also appear in the radiation once the temperature is high enough. Each quantum carries away a sliver of mass energy. The environment remains sparse because the radiation streams into near-empty space and redshifts with expansion. There is no surrounding gas to absorb the energy or to turn it into secondary light. Because the largest black holes have the slowest evaporation, they set the longest clocks. Supermassive black holes at galactic centers, with millions to billions of solar masses, define epochs measured in 10, 90 to 10, 100 years. By the time those clocks run out, any black dwarfs that could explode have done so long before. The only items left that can still do thermodynamics in the usual sense are the black holes themselves. When they finally finish, nothing with structure remains that can store energy in a way that is recoverable by a process. The particle bath is thin and cold. The expansion continues. The inventory is light, quanta, and quiet leptons, with occasional relics if protons do not decay. The effective temperature remains near zero. One puzzle that crops up at this point is the meaning of time. In physics, time is a coordinate that tracks change. If a state is truly static, no reactions, no flows, no internal rearrangements, what is time measuring? One view holds that time still passes because the metric of space-time continues to evolve with expansion. Another view holds that if no observer can track change and no system can act as a clock, then the notion loses operational meaning. The equations of general relativity and quantum field theory provide a parameter we call time. Whether that parameter keeps the same weight when there is nothing left to compare at different moments is a question we cannot settle with experiment. It sits near the same boundary as the Boltzmann brain discussion, a test of how far we can stretch definitions built for active, structured systems. If the vacuum could tunnel to a lower energy state, a different narrative would be possible. A nucleated bubble would sweep through or bud off, leaving a region with different physics. That new region might support processes that make structure again, perhaps even stars under a new set of rules. If instead the vacuum is absolutely stable, then no such transition occurs. The late-time map stays the same: cooling, evaporation, dilution. In both pictures, the segment that concerns black dwarfs and their rare supernovas sits far earlier on the extended timeline, folded between the end of the Stelliferous era and the long reign of black holes. After those last iron flashes, the sequence resumes its quiet progression. The quantitative waypoints are large but concrete. A solar mass black hole's evaporation time near 1067 years, a million solar mass hole near 1085 years, a billion solar mass hole near 1098 years. Hawking temperatures at nanokelvin and below for most of the climb, rising only when the mass is already tiny. Background temperature crossing below black hole temperatures near 10-20 years. Particle baths dominated by very low energy photons and neutrinos as expansion stretches wavelengths and thins number densities. If protons decay, additional light particles fill in over spans as large as 10-36 years or more. If not, hydrogen and heavier atoms remain as isolated wanderers. Each figure is a marker on a path defined by equations we test today at much smaller scales. The late picture brings back one more quiet detail. Even when no structured objects remain, gravity still shapes geometry. The metric of space encodes the energy density of fields and particles, and the expansion rate follows from that density. As radiation redshifts and matter dilutes, the terms in the equations simplify. The expansion tends toward a form set by whatever vacuum energy or effective cosmological constant the universe has. If that constant is truly constant, the large-scale behavior approaches a steady pattern of accelerated expansion. If it evolves, the late behavior tracks that function. The microphysics of black dwarfs and black holes plays out within that backdrop without altering it. After the last iron flashes, the system is simply in a regime where no large energy release is available and no engine can be built from available gradients. If any new structure appears, it must arise from fluctuations or from changes in the vacuum itself. If neither occurs, the contents are stable in the statistical sense. Photons coast, leptons drift. Relic compact objects, if any remain, cool and wait. The equations still have a time parameter. The fields still obey their wave equations. The average state remains a uniform, cold bath with no places to climb downhill from and no ladders to climb up. It is standard practice in physics to take the laws we trust, extend them as far as they can go, and read what the math implies. Sometimes the answer is quiet. Nothing much happens. Sometimes it is strange. Events occur that no one will ever witness. Black dwarf supernovas belong to that second path. They are what you get when quantum rules, gravity, and patience meet in a universe that has aged past every familiar light source. The implications touch how we think about time and change. One view says time is defined by change. If truly nothing changes, then time does not pass in any meaningful way. The long, cold future seems to fit that view until tunneling reminds us that change never drops to exactly zero. Given enough time, even in a near absolute zero world with no stars, probabilities add up. Somewhere, an iron-rich remnant crosses a limit and collapses. The event is not noise. It has a cause, a before and an after. That means the arrow of time still points in one direction, set by thermodynamics, rather than by the exact, reversible equations of microscopic motion. Entropy continues to increase. A black dwarf supernova is one more step in the long dissipation that began when the early universe was hot, dense, and low in entropy. The Big Bang gave structure room to grow. The far future spreads that structure thin. The last iron flashes release a final stash of stored gravitational energy, and then stop. There is another lesson about memory. The iron in a black dwarf's core is not a random deposit. It is the sum of countless tunneling events that occurred across ages stacked beyond counting. Each event is unlikely by itself. Together they are inevitable. Trace the chain backward and you find the original star on the main sequence, fusing hydrogen into helium. You find the red giant that shed its envelope. You find the white dwarf that cooled and crystallized. The black dwarf is the ledger that sums all of that. When it finally crosses the stability line and collapses, the outcome is the last entry in a story that began when that star formed. The times may be hard to imagine, but the logic is simple. Prepare conditions, wait, and let quantum odds do the rest. This picture also carries a small kind of fairness. During the age of stars, only the massive ones get classic supernovas. Small and medium stars end quietly. In the late universe, some of those once quiet lineages get a delayed chance. Not many, only those with remnants near the Chandrasekhar limit, but enough to matter in total count. Our sun is not among them. It will leave a white dwarf of about 0.6 solar masses far below the threshold. Cooling and tunneling can rearrange its interior, but they cannot add mass. It will become a black dwarf and remain stable for as long as atoms exist. You can imagine special cases, a white dwarf merger in the deep future, or some exotic path that adds mass long after galaxies have dissolved. The probability is so small that calling it unlikely is generous. Distances are too large, encounter rates too low. and the necessary conditions too strict. The rules allow the door to remain open in principle. Nature will almost never walk through it. The real candidates are heavy white dwarfs, born from more massive stars, remnants in the neighborhood of 1.2 to 1.3 solar masses. Their progenitors burned fast and hot, lived brief lives by stellar standards, and ended with cores already close to the limit where electron pressure fails. They cool like all white dwarfs, crystallize, and wait. Tunneling slowly builds iron in the deepest layers. Electron captures in dense regions chip away at the supply of electrons that provide pressure. When enough iron has gathered, and the electron gas has thinned past what gravity demands, collapse begins. The mechanism is not exotic. It is the same balance between gravity and quantum pressure that sets the line for ordinary white dwarfs reached by a slower road. Try to picture what witnessing such an event would be like if a conscious observer could exist in that era. The sky is not dark in the way we mean today. It is empty. There are no bright points, no glow, no dust, no arcs. The background temperature is effectively zero. Then, a point appears. It is faint by modern standards, perhaps 100th to 1,000th the peak luminosity of a type Ia supernova, but in an otherwise black field, it is stark. The light skews red, stretched by expansion that never stopped. The spectrum carries the marks of iron group elements and a few lighter products made in the shock. If you could break the light into colors with a simple spectrograph, you would read the story. A degenerate iron core exceeded its support and failed. For days or weeks, the point fades, sliding out of detection as the ejecta expands and cools. When it is gone, there is nothing left to watch. The next event in your region may wait for time so long that the word wait loses meaning. The arrow of time in this setting is not an extra rule. It is a statistical outcome. Microscopic equations do not prefer a direction. But when you start with many particles and special arrangements, the most likely path is toward more random configurations. That is the content of the second law of thermodynamics. The black dwarf supernova does not fight this law. It expresses it. The collapse and explosion convert a compact, ordered store of gravitational potential into heat and particles that spread out and become useless for doing work. The entropy tally increases. In that sense, the event is the last step of a long cooling one, more release on the way to a flat, near-empty distribution of energy. Questions about determinism sit close by. At the level of Schrödinger's equation or the equations of motion for fields, evolution is fully determined once you supply initial conditions. At the level of rare events over impossible spans, we talk in probabilities because we do not track every microstate. Tunneling rates are computed as chances per unit, time per pair. You multiply by the number of pairs and by the time available. When the time is 10, 1,000, 100 years or more, a tiny rate becomes a certainty in bulk. The detail we cannot predict is which specific black dwarf, in which region, at which precise moment. The law fixes the odds. The universe rolls the dice by waiting. It is natural to ask what this means for meaning itself. A lone flash in a universe without observers feels empty of purpose. Physics does not assign purpose. It assigns outcomes under rules. Yet there is value in seeing how far those rules reach. They carry structure from a star's birth to its last possible act. They carry the arrow of time from a hot start to a cold finish without adding new principles along the way. They connect scales, nuclear, stellar, cosmic, by simple bridges. Degeneracy, pressure, gravity, tunneling, conservation. If you want a lesson that stays close to science, it is that the same compact set of ideas explains beginnings, middles, and ends, even when end stretches beyond any human frame. There is a practical boundary to this extrapolation. We do not know whether protons are perfectly stable. We do not know whether the vacuum can tunnel to a new state or whether dark energy remains constant forever. We do not have a complete theory of quantum gravity to finalize the late phases of black hole evaporation. Those gaps do not erase the black dwarf picture. They bracket it. If protons decay on times shorter than tunneling-driven iron buildup, many black dwarfs will never reach collapse. If the vacuum tunnels and resets the rules, the late timeline changes. If nothing of that sort happens, the scenario stands. A small fraction of massive black dwarfs eventually cross the line and explode. Most do not. Black holes dominate later. Evaporation finishes the book. Names from our sky help to anchor expectations. Sirius A will leave a white dwarf near 1 solar mass too light. Sirius B is already about a solar mass too light. Procyon A and B will both leave remnants around 2/3 of a solar mass too light. Vega is likely around 1 solar mass as a remnant, probably too light. Systems with higher mass progenitors that avoid early core collapse and shed just enough to stop short of forming neutron stars can leave heavier white dwarfs of 1.2 to 1.3 solar masses. Those are the candidates for the far future. Even for them, the path is not guaranteed. Composition, lattice effects, and electron captures decide details near the threshold. As for totals, the numbers are both small in fraction and huge in count. If 1 to 10% of black dwarfs eventually explode, that is a tiny slice of the whole. Yet if your starting pool is hundreds of billions of stars in a large galaxy and over 1 trillion galaxies in the observable universe, the absolute count climbs. You can speak of 10, 21 iron supernovas over all space and time and still be describing a set that is sparse, separated by vast distances and vaster pauses. The experience of the universe, if one can speak that way, is not a continuous fireworks display. It is single sparks here and there, with long stretches of quiet in between. The imagined observer we placed in that future would not exist. Consciousness, as far as we know, needs gradients, flows, and structure. Free energy to be turned into work, steady supplies of low-entropy inputs, and mechanisms to keep complexity from washing out. Those conditions vanish in the deep future. The only gradients left are the brief ones an explosion creates, and they end too quickly to build or sustain minds. That does not reduce the reality of the events. It only tells us that the universe, at that stage, is a place where physics runs without witnesses. Even without witnesses, the chain has an internal check. The products of the final blast tell you what happened without you having to be there. Iron group nuclei in the ejecta, a neutrino pulse, a brief spectrum shaped by heavy elements, a light curve too dim to be a classic thermonuclear supernova. All are the footprints of a collapse that began when electron pressure failed in an iron-rich, degenerate core. The only thing missing is a logbook. The record is written in the arrangement of particles that remain, and in the energy that left as photons and neutrinos, stretched thin by expansion until it blends with the background. If you strip the story to its frame, the steps are spare. A heavy white dwarf cools. Tunneling reorganizes its core toward iron. Electron captures remove support. Gravity wins. Collapse forms a shock. A dimmer than typical supernova flashes and fades. Debris disperses. The region returns to near zero temperature and near zero density. The math behind each step lives in rules we use today: quantum exclusion, tunneling probabilities, equations of state for degenerate matter, general relativity for gravity, thermodynamics for the arrow of time. Extend them cleanly, avoid special pleading, and the far future reads like a quiet page with a few sharp marks. Black dwarf supernovas will be unobserved. Their light will stream outward into space that holds almost nothing to catch it. Photons traveling forever, redshifting into wavelengths so long that no instrument could ever have registered them. The events will not serve a purpose. They will not rescue a dying cosmos or kindle new life. They will occur because the equations that describe matter, forces, and space-time admit them as outcomes when you start with compact remnants and let time run without limit. That is the start point. The universe proceeds under rules. Whether anyone watches or cares is irrelevant to those rules. This is what physicists do when they ask about the ultimate future. They take the pieces we have tested: quantum mechanics, general relativity, nuclear physics, thermodynamics, and extend them into regimes of long time and low energy. Sometimes the math says nothing happens. Sometimes it says rare things happen, but only after spans that bury all clocks. Black dwarf supernovas fit the second case. They are not special targets the universe aims for. They are allowed consequences of the Pauli exclusion principle, the Heisenberg uncertainty principle, the behavior of the strong and weak forces, and gravity's compression given a degenerate star and a timeline measured in 10, 1,000, 100 years. There is a subtle lesson about laws and possibility. Physical laws are constraints, not scripts. They do not appoint a date and place for an iron supernova in a black dwarf. They set the boundaries of what can happen and assign weights to each outcome. Within those boundaries, probability rules. Over everyday spans, a tunneling reaction in a cold, solid core is fantastically unlikely. Over a span with 1,100 zeros, the product of small probabilities and huge time becomes decisive. The universe, left to itself, explores possibilities. It does not visit all of them, limits still apply, but it visits many that look impossible on shorter scales. That leads to hard questions about probability when time feels unbounded. Does eventually mean every allowed event occurs? Not necessarily. Probability measures chance per trial or per time, not a guarantee of appearance. Some events may remain so suppressed that, even with unthinkable time, the expected count stays below 1 in any finite region. Others, like tunneling steps up the nuclear binding curve inside a black dwarf, accumulate. The distinction matters because it marks where physics stops making promises. It can tell you which doors are open and how wide. It cannot promise which door the universe will walk through in one isolated patch of space. A different uncertainty lives in the constants themselves. Some theoretical efforts allow the strengths of forces or particle masses to vary over cosmic history. If the fine structure constant drifted, or if the strong force changed slightly, tunneling rates would shift. The Chandrasekhar limit depends on fundamental constants. If those changed, the threshold would move. Right now, observations suggest remarkable stability. Spectra of ancient light, atomic clocks, and other tests have not revealed convincing drift in constants. Extrapolating that steadiness, the picture with black dwarf supernovas follows. If, however, new physics appears on vast timescales, if constants creep or unknown particles dominate, our forecasts could be wrong in detail or in kind. That is not a flaw in the method. It is a boundary of knowledge. Proton decay is the most concrete fork in the road. grand unified theories often predict that protons are not forever. Experiments have pushed the lower bound on the proton lifetime to 10, 34 years or beyond, but have not seen a decay. If the true lifetime is, say, 10, 36 years, then protons vanish long before a black dwarf can tunnel its way to an iron-dominated, near-limit core. The remnant's material dissolves into lighter particles over eons, skipping the late collapse. The universe moves from a landscape of cooling remnants to a bath of radiation and leptons, without the coda of iron flashes. If, instead, protons are stable far longer than 10, 1,000, 100 years, then black dwarf supernovas become the last significant energy releases. Either way, the far future view converges. A thin, cold, expanding expanse with little structure and long pauses between sparse events. By human measures, that outcome looks bleak. We live in the Stelliferous era, a window crowded with gradients and patterns. Our senses and minds evolve to track change, find structure, and extract energy from differences. A uniform, near-zero temperature universe lacks not just biology's raw materials, but the thermodynamic footing complexity needs. The lack of interest is a fact about us, not about physics. The universe is not trying to be meaningful. It began in a low-entropy state, allowed structure to arise, and is relaxing toward higher entropy. The math does not include a clause for fascination. That does not mean meaning is impossible. Meaning is something observers build inside localized pockets where gradients exist. Our existence is evidence that such pockets occur. Stars formed, heavy elements accumulated, planets cooled, chemistry unfolded, minds emerged. Doomed to heat death is not an argument against local value. It is a statement about boundary conditions on the longest scales. Black dwarf supernovas reinforce that point in an odd way. Even when the broad canvas is nearly blank, the rules still permit changes. A quiet lattice can move by tunneling. A cold remnant can cross a limit. An explosion can follow. The arrow of time keeps pointing, defined not by any one clock, but by the aggregate drift toward higher entropy. These events also underline how the present is connected to the remote past. An iron supernova in the Age of Quiet does not spring from nowhere. It is the end of a line that began with a star's birth, continued through fusion and mass loss, carried through the crystallization of a white dwarf, and preceded by quantum odds across ages. The final collapse records all of that history. The star's original mass set the remnant's mass. The remnant's mass set how close it sat to the Chandrasekhar limit. The lattice and composition set how tunneling unfolded. The weak interactions set when electron captures bit into electron pressure. The laws did not change, the context did. You can stretch the thought further with the Sunday, its remnant, at roughly 0.6 solar masses, sits far from the critical limit. Alone in an expanding universe, it will never gather the missing mass, and tunneling cannot supply it. The scenario that lets it burst as a black dwarf requires a contrivance, a merger or accretion process vanishingly unlikely after galaxies dissolve and distances grow. The rules permit it in principle. The cosmos will almost never arrange it in practice. That contrast possible in math, absent in history, shows why allowed is not the same as expected. Massive white dwarfs, by contrast, are born closer to the line. Remnants of 1.2, 1.3 solar masses originate from heavier stars that lived fast and died young. They cool, crystallize, and weight. Tunneling creeps their cores toward iron. Electron captures shave the electron supply. Eventually, a few cross the limit. Collapse follows. The light is dim by the standards of the bright universe, but absolute in a dark one. A red-shifted flare, a whisper of neutrinos, ejecta rich in iron group elements, and then silence. The next flare may be unimaginably far away in both space and time. The philosophical questions that orbit this picture about determinism, probability, and the meaning of end do not change the physical sequence. Microscopic equations are time reversible, but macroscopic evolution has an arrow because overwhelmingly more states look disordered than ordered. That statistical arrow is what carries a black dwarf from a stored, compact arrangement of mass and pressure to dispersed, low-grade energy. Determinism at the level of equations coexists with uncertainty at the level of events because we summarize huge ensembles with probabilities. Given initial conditions, the distribution of outcomes is fixed. Which outcome a single isolated region realizes can remain unknowable and, in any practical sense, random. If protons do decay, the late map edits out iron supernovas. If they do not, those supernovas provide the last major entries. Beyond that fork, the rest is quiet in either branch. Black holes evaporate on times that make even 10, 1,000, 100 look tame. Photons and neutrinos drift apart as the expansion stretches their wavelengths. If the vacuum is absolutely stable, the background approaches a steady state set by the cosmological constant. If the vacuum can tunnel to a different state, patches with new physics can bud or sweep through. We do not know which version the universe chooses. What we can say, staying close to tested laws, is that the same compact set of principles, exclusion, uncertainty, nuclear binding, degeneracy, pressure, gravity, thermodynamics carries the story from bright beginnings through quiet endings without adding new axioms. There is one more angle on ending. The word implies a stop, but the physics suggests a transition. From eras where macroscopic engines are easy to build to eras where only microscopic moves remain. From skies full of stars to skies with solitary flashes. From broad, fast changes to rare, slow ones. Quantum mechanics guarantees that nothing is perfectly still. Every barrier has a non-zero chance of being crossed. That is why black holes evaporate, why proton decay stays on the table, and why black dwarf supernovas exist in theory at all. The universe we see is a frame cut from a reel, not the final slide. Changes continue, at first constantly, then sporadically, then almost not at all, and still not quite never. The light from those rare iron bursts will go somewhere. It will thin, stretch, and fade until it loses any practical identity. The act will remain what it always was, a lawful conversion of compact, supported matter into freer, lower-grade energy. No monument will stand where it happened. No catalog will list the date. The ledger is written in conserved quantities and in the slow tilt of entropy. Physics keeps the books even when the room is empty. We live during one brief phase of a much longer process, and that process runs on with or without us. Black dwarf supernovas are reminders of our temporary place and the universe's persistence. They show that timescales exist far beyond intuition, and that physical processes keep working across those spans. Whether anyone observes them or not, they are the long-term consequence of stellar evolution, the final expression of how matter behaves under gravity and quantum rules. when given more time than any clock we use can track. They also expose how our intuitions about the end mislead us. We picture a finish line and a permanent stillness. Physics offers something else. No configuration is perfectly final. Every arrangement of matter and energy carries some non-zero chance to become a different arrangement. Given enough time, the improbable accumulates. Eras hand off to new eras, not because purpose drives them, but because the equations allow transitions. The age of stars yields to an age of remnants. Remnants yield to the long rule of black holes. Black holes yield to the dark, and the dark may in turn yield to futures we cannot yet map, if deeper physics permits it. A black dwarf supernova is the exclamation point. At one of those handoffs, a last light before a quieter page turns. No people will be there, long before any black dwarf has cooled enough to begin the slow climb to iron. The sun will be gone as a star, Earth dismantled, and every trace of our culture erased by time and heat and drift. Between our epoch and those explosions lies a gulf without words. Yet we can outline the steps. Mathematics and measurement let us project forward. Stars fade. White dwarfs cool and crystallize. Quantum tunneling, given ages with 1100 zeros, adds iron grain by grain. Electron pressure fails in the densest cores near the Chandrasekhar line. Collapse and a muted detonation follow. We cannot watch, but we can know. That knowledge binds our moment to the deepest cadence of the cosmos, to rhythms that stretch over billions of trillions of our years. From a hot, dense beginning 13.8 billion years ago, the universe expanded and cooled. Atoms formed, the first stars lit, galaxies took shape, planets assembled, chemistry deepened to biology on at least one world, minds arose. Now some of those minds can run the film forward as well as back. In thought, we can witness the last stars go out, white dwarfs dim into black, iron cores gathering in the quiet, and the rare, final flashes those cores release when gravity overtakes electron pressure. This is beyond direct observation, but not beyond inference. It rests on tested laws, extended with care. The ability to draw such a line across scales and ages that dwarf us shows the reach of reasoning joined to evidence. Black dwarf supernovas push that reach to its edge. They require us to bridge 1,100 orders of magnitude in time, to trust quantum effects that are vanishingly rare yet certain given unbounded weighting, and to merge general relativity, nuclear physics, thermodynamics, and cosmology in a regime where each is stretched thin. Even so, the outline holds. We can estimate when they begin, how bright they would be, and what their spectra would say. We can explain why they are fated in a universe where protons last and constants hold. We cannot see them, but we can account for them, and that accounting is a quiet triumph of the method that built modern science. So here we stand, 13.8 billion years after the Big Bang, considering lights that will not rise until 1,100 years have passed. The span between now and then makes the entire history to date less than an instant by comparison. Yet the same compact set of ideas, exclusion, uncertainty, binding energy, degeneracy, pressure, gravity's pull, entropy's arrow, lets us track the path to those final flares. Black dwarfs do not exist yet. They will not exist for quadrillions of years. They will not explode for ages beyond any practical counting. But the conditions that produce them are already part of the story. Stars are forming the white dwarf progenitors now. Those remnants will cool, their cores will harden, quantum odds will do their slow work. And someday, far past anything that concerns life, the threshold will be crossed. When that happens, a pinpoint will appear against a sky that is not merely dark, but empty. It will be faint compared with supernovas of the bright era, yet absolute in a universe without other lights. Its spectrum will carry iron's signature, stretched by expansion. For a few days or weeks, it will burn, then it will fade to the same black it disturbed. No eyes will mark it. No instruments will record it. The photons will travel outward, stretched thinner and thinner until they blend with the background. What will remain is the fact of the event, a lawful conversion of compact matter into freer energy. One last adjustment, honored by the equations that have governed every step since the first second. If protons do not survive that long, the path edits itself. Matter dissolves into lighter particles first, and the iron flashes never arrive. If constants drift, the thresholds shift and with them the timeline. But if the laws hold and protons endure, then black dwarf supernovas are the true final acts of stellar matter. They do not change the ultimate trajectory toward a thin, cold bath. They mark its last punctuation. Afterward, only black holes carry clocks forward, and then only through evaporation that draws out over 10, 90-10, 100 years. In either branch, the late map is spare, expansion, dilution, and the slow bookkeeping of entropy. None of this lends purpose to the universe. Purpose is something observers make locally while gradients and structures allow it. What the picture does provide is continuity. It shows how the same rules that let stars ignite also let their corpses, given enough time, find one more way to change. It shows that ending in physics is almost never a wall. It is a limit, approached by smaller and rarer moves. Even at the far edge, when engines are gone and clocks have few ticks left to count, probabilities still open paths, and nature still walks them. Black dwarfs do not exist yet. They will. They will explode. When they do, the cosmos will prove once more that age does not annul law. In an emptiness that has forgotten galaxies, a degenerate iron core will exceed its support, collapse, and light the dark for a moment. The light will pass. The region will return to silence. The universe will be almost what it was, except that one more remnant will have finished its arc, and one more trace will have been written into the background. One more star will have had its day, even if that day arrived 1 trillion years too late.